Brilliant.
So let's start.
Can I just remind everybody, I'm about to mute myself, so if I can remind everybody on the call to make sure that they are, please, that would be really helpful.
Okay, this is the contents. I'm not going to go through them. The whole presentation is essentially something that you can read at your leisure. There are a lot of notes which I cannot read nowadays because I have problems with my eyesight. So you can read it at your leisure, and if you have any problems or questions, you can get in touch with me. So the key is for a successful applied geochemical project at any mapping scale is efficient planning. This is especially if you are going to do this work for a company, okay, because you have to be cost effective. Every applied geochemical survey at any scale has these 9 stages: planning, sampling, sample preparation, storage of samples, laboratory analysis, quality control, data processing, map plotting, interpretation, and report writing. Now, if you fail to perform any of the aforementioned steps, then you may have problems. So the aim of this seminar is to show you that well-tested applied geochemistry methods can be used not only in mineral exploration, but also for environmental and medical purposes, and that data interpretation varies with the objectives of the geochemical survey. Of course, something that you must remember, the applied geochemistry methods should be adapted according to the objectives of the geochemical survey. Now, something that I would like everybody to consult is 5 publications. This one is Applied Geochemistry, the How and Why. Essentially, it's a tutorial for applied geochemistry. You can read the comments by David Smith. Oh, why doesn't it change? And this is comments by Ariadne. The second book is the IUGS Manual of Standard Methods. It has a lot of material there, and also there are supplementary data, and of course there are where the chapters can be downloaded, the whole book, and also the word text and original figures. Now, if you are going to perform urban geochemical mapping, there is a manual which we have written a few years ago, 11 years ago. And there is also an appendix which is very useful about the chemical characteristics of contaminating activities. Now, this is a textbook with many chapters, which I recommend that you or your library to buy it. It has a lot of case studies, and it's a very good reference work. Now, another reference is the urban geochemical mapping. There are several papers, and one good thing that these papers have are the original data sets as well as the quality control. So it's again useful for teaching purposes. Now, here are the stages of phase geochemical mapping survey. I'm not going to go through it. You can look at it at your leisure. And there is another heavy. And this is for a typical approach for contaminate land or property investigation. The steps are similar, but since the, let's say, terminology is different, I thought it was a good idea to have a different sort of flow chart. Again, you can study it at your leisure. Now, to produce high-quality, harmonized data sets, there are three stages that you have to be careful: sampling, sample preparation, and laboratory analysis. Now, sampling and sample preparation are the most crucial stages of any geochemical survey. Any errors during these two stages is carried forward and can result in the failure of a whole survey. Now, laboratory analysis is important, but if you don't sort of get the results right, they can be corrected by reanalysis of samples, provided there is enough sample material available. So it's your job to have enough material for subsequent analysis if something goes wrong in your project. Now, the main job of the applied geochemist is to ensure that the field and laboratory procedures, sampling, sample preparation, and chemical analysis are applied correctly, and the produced data are of high quality and integrity. Interpretation of the result is completely another matter, and it depends on the training and experience of the applied geochemistry, and also for the purpose the geochemical survey is being carried out. Now, for a realistic assessment of contamination, it is significant to have high-quality geochemical baseline data about the natural element variation before humans began to contaminate the environment. So we have this sort of equation, you may say. The geochemical anomaly is equated with the natural variation of an element, which is due to the lithology. And in mineral exploration, we term it as background. And there is also abnormal concentration of element due to mineralization and lithology. Okay, essentially, this is the geochemical baseline. Now, on top is the geochemical baseline, and we have anthropogenic pollution or contamination, which is the natural geogenic variation of an element, plus the concentration of element from anthropogenic activities. Now, these are some of the definitions which are very good for you to have in mind, and it's a long history. According to COVID, I don't know if some of you met him. I have, and he was a good friend. He has defined geochemical anomaly. It is necessary to consider the value of the measured parameter, the physicochemical nature of the sample material, the physicochemical environment from which the sample is taken, and the spatial distribution pattern of the measured variable. Hence, he arrived at the following appropriate definition of a geochemical anomaly. An abnormal high or low content of an element or element combination, or an abnormal spatial distribution of an element or element combination in a particular sample type in a particular environment as measured by a particular analytical technique. Following the above definition given to the geochemical anomaly by COVID, background and thresholds depend also on the particular sample type in a particular environment as measured by a particular analytical technique. Now, again, according to COVID, an anomaly cannot be recognized unless background can be defined. The constant of any element in any geological material cannot be represented as a single number. Apart from variations due to error in sample preparation and analysis that are inevitably present in the reported value for a particular sample, there is an inherent variability in the content of an element even in a small and petrologically homogeneous granite or in B-horizon soil samples overlying an homogeneous rock. In statistical terms, the recognition of an anomalous sample depends upon establishing the statistically probable range that occurs in the background population, and calculating for some defined confidence level an acceptable upper limit, the threshold, of background fluctuation. Any sample that exceeds this threshold, which is the lowest anomalous values, is then regarded as possibly anomalous and belonging to a separate population. Similarly, for negative anomalies, threshold defines the lower limit of background fluctuation. Now, the first definition of background was given way back to 1957 by Hopkins. The abundance of an element or any chemical property of a naturally occurring material in areas where the chemical pattern has not been affected by the presence of a mineral deposit. Then Hawkes and Webb in 1962 modified the background definition to the normal abundance of an element in barren earth material and elaborated further. For any particular element, the background value is naturally likely to vary considerably according to the nature of the earth material in which it occurs. Furthermore, the distribution of an element in any particular class of material is rarely uniform. Thus, it is usually more realistic to view background as a range rather than as an absolute value. Hawkes has also defined threshold with respect to geochemical prospecting as the limiting anomalous value below which variations represent only normal background effects and above which they have significance in terms of possible mineral deposits. So, geochemical anomaly or anomaly is an abnormally high or low content of an element or element combination, or an abnormal spatial distribution of an element or element combination in a particular sample type and in a particular environment as measured on a particular grain size, I stress that, by a particular analytical technique. Also, background is the non-anomalous concentration range of an element or element combination in a particular sample type again and in a particular environment as measured on a particular grain size by particular analytical technique. And threshold is the limiting anomalous value of an element or element combination measured in a particular sample type and in a particular environment as measured on a particular grain size by a particular analytical technique, below which variations represent only normal background effects and above which element concentrations are significant in terms of potential mineralization or environmental contamination. Now here we see a conceptual model. We have an ore body, okay, and we have a halo around it, okay, and we have the background at the back. Now, if you take samples at the top there, you have a curve which shows the background results here. Then you have the halo with elevated concentrations, okay, and then the anomaly is directly above the ore body. Now, if you replace the ore body with a contaminating source, you may similarly sort of define the anomaly with respect to the contaminating source. Now here we see, you can read everything on the right-hand side. I will just explain the cross-section. This is a primary dispersion in rock samples in the Lavrion area. Here is a mineralized area, in fact, in the area. And as you can see, you have the variable background here, okay? And as we approach the anomaly, we reach the upper background limit, okay? And then also the threshold is very narrow, okay, and the anomalous concentrations. Okay, this is how we define the anomaly. Now, this is more complex. I'm not going to go through it. You can sort of study it at your leisure. It's as you can see, it's a section on the islands of Chios, and the section below shows how the anomaly and background and the halo are defined. And you can study this at your leisure. Now, we said that there are differences depending on the sample type. Now, we see here the same area, Lavrion, where we have the rock, the primary dispersion, and we have the overburden samples with the secondary dispersion. Now, if you see the sections below, and of course the geochemical maps, there are distinct differences, especially in the level of concentrations. If you see the maximum concentration in the rocks is 1,860 ppm, whereas in the overburden sample is almost 15%. Okay, so you can see that the anomalous range, the background variation, the halos, let's say in numbers, are completely different. So this is why one has to be careful when is defining these terms to say in which material it is defined. Now, here I just show you the results of the agricultural soil samples, which are from the GEMAS project. They have been analyzed by 3 different analytical methods. The MMI is a cold analytical method. The AR is a hot aqua regia method, and of course XRF. And as you can see, there are different results, okay, according to the method. Okay, so when we define something, again, it depends on the analytical technique used for that particular sample type. Here we have agricultural soil, and the differences, as you can see, are quite distinct. Now here we see the map with the cold MMI. We see here the map of aqua regia. Now, if you compare it at your leisure, you will see there are differences. For example, a distinct difference is in Italy, in central Italy, where there are anomalies in the aqua regia, whereas in the MMI, there are no anomalies. Now, this is the XRF, again, comparing with the MMI. Again, you can see differences. And here we have the aqua regia on the left-hand side this time with the XRF. And I just marked the differences so you can see them, okay? Now, something that everybody has to be careful, especially if you are sampling soil. Everybody thinks soil is easy to sample. Now, the mistakes that are being made is you sample depth-related samples, okay? And this is a mistake because every soil horizon has different geochemical characteristics, okay? So one has to be very, very careful. For example, here we have a non-significant geochemical anomaly because this fellow has sampled at a constant depth, And as you all know, lead is enriched in organic soil, so we have an anomaly. Now, if you sample consistently the same soil horizon, okay, which means that you had to dig down to the soil horizon to avoid the organic topsoil layer, what you see here, there is no geochemical anomaly. So you have to be very careful of how you plan your sampling. Now, as I said at the beginning, since this is a SEC Fellow seminar, and also we have people, colleagues from the IMGA, I have decided to show you a contamination case study way back from 1996. Unfortunately, the results are confidential, so the exact name and location will not be given. Now, the case study is at disused dry-cell battery factory, and from what they told us, they did not produce any nickel cadmium batteries. Now, the objectives: to determine potential contamination of soil and groundwater by such elements as mercury, zinc, manganese, lead, cadmium, also copper, cobalt, antimony, arsenic, and nickel; to determine the depth of contaminated soil, and also to estimate the volume of contaminated soil. And the mapping scale was 1 to 5,000. It's a very detailed scale. 1 centimeter is 50 meters on the map. 1 centimeter on the map is 50 meters on the ground. Now, the information provided by the company was not much. It was just the plan of the factory building and the industrial product without any coordinates. The plant produced dry cell batteries for 23 years, from 1969 to 1992 in 2 phases. 1969 to 1981, production of dry cell batteries which contain mercury, zinc, manganese, and lead. And from 1981 to 1992, production of dry cell batteries which contain zinc, manganese, and lead. And again, the second period, as you can see, there is no mercury in the dry cell batteries. So we had to carry a preliminary investigation, a site reconnaissance of the site with 1 to 50,000 and 1 to 5,000 topographical maps for recording the exact location of the battery factory. The factory site was situated on a comparably flat surface, in fact on the floodplain of second-order streams. The surface soil varied from silty clay to sandy silt and was moist and covered by grass and other bushy vegetation. Sheep were grazing on the neighboring field, and according to information from the factory worker, they also grazed on the land of the battery factory. The dominant wind directions, according to the local weather station, were from the northwest and west, with the latter being the most dominant. So we had to carry a bibliographic research about the materials used for the production of dry cell batteries, just to see if there was anything else that the company was not telling us. Usually companies keep secrets. You must remember this. Now, the 1 to 50,000 geological map showed that the industrial area is covered by tertiary Holocene riverine alluvial sediments, comprising mainly marl, clay, sand, and conglomerate of lower Pliocene age. The marls and clays have a high carbonate content, since it is anticipated that the soil samples will have high concentration of calcium, which was subsequently verified by analysis of the collected samples. Now, we also had the hydrogeological map, and there we have seen that there is a proportion of clay high at some point, resulting in comparably impermeable cover with stagnant water. The water level in the borehole to the east of the property was at a depth of 62.2 meters, and the one to the northeast was at 27 meters. Whereas the groundwater in the study area appears to be about 1 meter below the ground surface, based on observations from storm drains around the building, provided, of course, they were connected to the local aquifer. Now, the assessment of contamination by the dry cell factor is slightly complex when other nearby contaminated sources, roads and railway, emit almost the same elements such as lead and zinc, plus iron and cadmium. However, the potential contamination from the dry cell factory is more complex, with lead, mercury, cadmium, manganese, zinc, antimony, and arsenic. Hence, this difference will be used to distinguish the contamination caused by the roads and railway from the more complex factory contamination. Now, a key issue was the factory chimneys. They were only about 1 meter above the roof. Hence, it is not expected that the aerial contamination from the sequel emitting chimney would have traveled a long distance from the factory. There were another 4 chimneys, but they were not. They were for aeration, and they were not emitting any contaminants. Now, this was essentially the plan. You see the battery factory building. This is the emitting chimney, the railway, the main road, and the secondary road. And based on the collected information, a conceptual site model was developed. Again, you can study this at your leisure. We had all the information from the site. So we assume that there is contaminated soil. We did not test it yet. Now, if there was contaminated soil, we have also contamination of air from the emitting sources, contamination of soil water, contamination of groundwater, and also the other routes here. I'm not going to go through everything. You can study this at your leisure. It's a good exercise for you. And this is the time for thinking. Now, I produced this with the Microsoft Copilot, to be honest. I only use it for producing these diagrams, which are very good. I don't use it at all for writing text because I still like to think of what I'm going to write. Since the assessment of contamination should be done in a cost-effective way to reduce the rehabilitation costs, different schemes were tested. Square blocks of 50 by 50, 25 by 25, 20 by 20. Now, the 50 by 50 and 20 by 20 block schemes were rejected because the first would be too costly for remediation, and the second, too dense, as many samples would be collected. Now, the 25 by 25 meter blocks appear to be the most cost-effective and best suited to the geometry of the factory area, as you will see. See the factory building, and these are the 25 meter blocks. 25 meter blocks, which fairly fit the battery factory building. As you can see around it, there are 1, 2, 3, 4, 5 25 meters on the north side and 4 on the south side. So this was a really good plan. And because we wanted to see the contamination from the railway line and the main road, and also the secondary road to the south, we had to extend the blocks outside the area of the factory. Now, as you can see, we use a random number system in all the blocks. Now, in those days, in 1996, the 102 random number sequence was generated using an in-house Fortran program. Nowadays, you can use a program online for randomizing your samples. And this is something that you must always do when you plan your survey. You should plan it well to know how many samples you will be taking, okay? And it's a good idea to add a few extra numbers just in case you are going to collect a few more samples and randomize them. This is the best way because I don't like randomization of the samples after they have been collected. This is something that we have done with the GEMAS project, and it was a nightmare because we had to be very, very careful when we had to back number the samples. So it's better to randomize the samples before you start sampling. Now, a 3-stage survey was proposed to the company management. Orientation survey mainly to determine the depth of the soil contamination at selected sites. Square block sampling, and after the evaluation of the results, sampling of contaminated blocks down to a depth of 100 centimeters. The company did not like our plan. Well, I always like to carry out an orientation survey. They wanted to shorten the investigation. Okay, it was their problem because they were paying. And of course, you tell them the reasons that you wanted to carry out the orientation survey. But since they are paying the expenses, they take the responsibility for any mistakes made in the subsequent stages. So they wanted us to go directly to the square block sampling, and after the evaluation of the results, to sample the contaminated blocks down to 100 centimeters. They have given me one local worker to assist me in the sampling. And of course, we had to lay out the grid. And they did not want us to sort of, everything to be seen from the outsider. Usually we use wooden pegs and we paint them on top of red and we write the name. And of course, this can be seen from a distance as well. So we had to do it somehow inconspicuously. So the only solution was to use 10 centimeter long steel nails with a short red ribbon tied on the top and to write the site number on the ribbon with a black permanent ink marker. Now we use a compass and a 50-meter steel tape measure to measure the 25-meter distance between the sample sites. And this G17 was the reference starting point. Now, sampling with an ochre in Mediterranean countries is something that is not usually done because the soil is usually dry and lacks sufficient clay to retain the sample as the ochre is withdrawn from the hole. Now, fortunately, in this particular case, the soil was moist and its clay content was adequate for using an ochre. So soil sampling of the first 20 symptoms was performed with a 1.5-inch ochre and the deeper samples with 1-inch ochre. Now, this is the other equipment that we had to buy. Okay. I'm not going to read it, so you can read it at your leisure. And here we have the map showing the square block sampling scheme over the battery factory. The composite samples were about from 0 to 20 was about 1 to 1.5 kilograms, and they were collected from the 4 corners of each block and the fifth sampling site was randomly selected within each square. Now, I call this a rolling sampling scheme. Why? As you can see, the red arrows at the corner of each square, they have small pointed arrows. Okay. So each sample from each sampling point was subdivided into 4 equal parts. Okay. And so this sample here, for example, number 100, okay, it was made up from portions of the sample site at the sample site at the corners and the random site within the square. Okay. Now, because I was not really satisfied with the directions with that the management of the company, I decided that it was a good idea to take the deeper samples at one area where there was stagnant water, and this was at this around block 52. Okay, so the samples were taken down to 80 centimeters, and because, as I said, this was a waterlogged site, and also it was the temporary disposal and storage area of the factory's solid waste. So if anything bad went on, it should be on this particular block. Now, the 26 thick propyl soil samples were taken with extra care to avoid any cross-contamination. Always the auger and plastic scoop were thoroughly clean. Oops. Before collecting the next sample. All soil samples were placed in pre-number resin bags, and the pre-number card in the small self-sealed plastic bag was placed on the top of the sample. The bag was secured with a plastic strip lock, and for safety during the transportation, the resin bag containing the soil sample was placed in a strong plastic bag and secured again with a plastic strip lock. And here, again, I have photographs, to be honest, of the sampling procedure, but they're on slides, and they're somewhere in my archive. And it was impossible to retrieve them. So I instructed Microsoft Copilot 365 to make the 2 images on the right-hand side and to place the sample on in a plastic sheet like I have done. Okay, I mean, you can imagine the sample was in blocks, and anyway, it was difficult for the Copilot to do it exactly. But anyway, you get the idea. The lumps from the retrieved cores were broken up, and in fact, what I used to do is to leave them exposed to the atmosphere in order to dry, and then come back to sort of break them up and try to homogenize them as well as possible. I mean, the homogenization you see on the right hand there is too ideal. I mean, I could not really do it such fine grain. But anyway, it was sufficiently well done for to satisfy my let's say professional etiquette. Now, the 102 surface soil samples were placed in consecutive number order and sent by the company together with the 10 duplicates and 16 profile soil samples to OMAC laboratories, now part of ALS laboratories. I forgot to say that we always take field duplicates, and I always take 10% of the duplicates. The sample preparation, the soil samples were dried in thermostatically controlled ovens at a temperature of less than 35 degrees because mercury is sensitive to higher temperatures. After drying, the soil samples were desicced in a porcelain mortar with a porcelain person and sieved through 80 mesh screen. This is again what we have used in the Institute of Geology and Mineral Exploration. After several orientation surveys, this is what we thought at that time was the best size for analysis. We used it also for stream sediment and also for soil. Now, the laboratory analysis of soil samples, in those days, it was with atomic absorption spectrometer. Again, we selected a sample procedure with a high sample weight, 4 grams of the 80 mesh fraction was digested by hot aqua rigger, and the calcium, cadmium, copper, iron, magnesium, manganese, nickel, lead, and zinc were determined by double beam atomic absorption spectroscopy. Arsenic and antimony were determined by high regeneration apparatus, and mercury with an AES flameless reduction method. The pH of the soil was also determined. The laboratory analyzed every 10th project sample as well as international and internal reference materials and method blanks. The battery factor contaminant is caused by the following elements. Okay. In addition, we have calcium, iron, and manganese to determine. Calcium, it was to sort of verify that it exists, and because it restricts the mobility of contaminants in solution. Iron, this purpose was to ascertain whether the contaminants are absorbed onto iron oxide, since in such case their release is somehow hindered. Magnesium, high concentrations of magnesium in soil have the property of hindering the uptake of chemical elements from soil, according to Kofetal 1979. Now, you receive the analysis.
Alecos, we've got just over 5 minutes left, so if I can ask you to move on to give chance for questions, that'd be really great. Sorry.
Okay, I'm almost at the end. Now, as you can see, we look at the results, and the first thing that you see, we have a high lower detection limit for mercury. So we asked the laboratory, why is this? And they discovered that they reused agents with a 50 ppb mercury. So they had to reanalyze all the samples and for the other elements as well. Okay, this was the insistence because it was their mistake, and we did not know how this would affect the other analysis as well. And as you can see, the mercury analysis with a lower detection rate at 10 ppb is much, much better. Now, we use an ANOVA design, and I always prefer the balanced ANOVA, okay, where we split the routine and field duplicate samples into 2 subsamples, and we finally have this very nice pie diagram where we have the sampling. Okay, I did expect that we will have a high sampling variance because mercury was not sort of distributed equally in everything. The analytical variance is very good, and we have a good geochemical variance. And as you can see, we had to take the residential limit at that time because the company said that the plot may change from industrial to housing estate. So as you can see, this is the area that has been contaminated by mercury. And of course, we use a probability method. You can see it at your leisure. And as you can see, we have a different picture because we have the contamination, actual contamination, the probably contaminated are the red blocks, and the possibly contaminated is the pale brown. And this is where we carried out the deeper sampling. Okay, these were the blocks that needed more attention. And something that, again, we had to ensure that we have comparative results between the May and August. We reanalyzed 10 samples in the batch of the deep samples. 8 groundwater samples were collected, and we did not see any elevated concentrations. So that was good. The emission of potential elements during the production of dry cell batteries and essential waste such as paper, impregnated, and caused the aerial transportation and deposition of toxics, mainly mercury and zinc, in soil to the eastern part of the factory because of the prevailing westerly winds. The soil pressure showed that toxic element contamination is primarily in the first 20 centimeters of soil and gradually decreases with depth. Transport to lower soil layers occur in areas where rainwater accumulates. Mercury and zinc appear to be loosely bound on the iron manganese oxide in soil, as indicated by their low correlation coefficient with iron and manganese, and are also possibly adsorbed to clay minerals. It was concluded that although mercury and zinc contamination of soil is significant, the risk analysis indicates that their spread and environmental impact effects are low, since the property is in an industrial area and the groundwater has not been affected. Soil remediation is not necessary, unless, of course, it is changed to the land use is changed. Now, this is for you again for further reading. I recommend that you download the quality control reports of the GEMAS project. They are here. And also, very important, for you to write a good geochemical professional report. The Association of Applied Geochemists has this very nice guide which you can download. And also this video will be uploaded by Oliver. And also you can download usually the PDF file, but you can also download the original PowerPoint presentation by using the following hyperlink. And thank you very much.
Thank you, Alecos. That was absolutely great. I actually make a couple of comments before I open it to the floor. Firstly, to say, then that slide which you currently have up actually very much reflects what we would do within the health industry as well. I use the word industry lightly but advisedly. And I'd also like to say what you have just given to us is really, really important. I'd comment on that as an editor for papers to say we really need to look at work which is being carried out to that kind of depth and care, because very often it's missing. So let me, without further ado, open to everybody else. Now let me see if I can bring that across so I can see everybody. I can only see a few people. Do we have any questions, please?
Oh, there must be some questions.
David,
I was not so good.
Go for it, please.
Well, thank you for a lovely talk, and especially the references. It's so important for us to be able to look at those afterwards. I'm just wondering a question about, much of this is predicated on assuming a uniform background or just one distribution of background values. And I'm wondering if you have any thoughts or experiences where you've been on sites where there are clearly like maybe 2 different soil types or 2 different geologies. So in order to be able to determine an anomaly, you need to account for different types of background. Do you have any advice on that?
Yes, that's more complicated, David.
Yes.
That's the problem. That's why you need to carry out this is what I strongly believe in. You are describing essentially a complicated case, and you need an orientation survey to begin with. Because the orientation survey will give you all the elements that you need to plan the detailed investigation more correctly. Now, if you do not do the orientation survey, you will not be able to define, as you say, the geochemical variation of your background, the one background area or the second background area or the third background area, because nature is more complicated than most of us know when you are in the field. Now, this particular case was quite simple, to be honest. Now, the problem here was how to estimate the volume of contaminated material in case they had to rehabilitate. That was the key issue here. That's why I chose this rolling sampling technique. But yes, you are right. You need to be more careful, and you need definitely an orientation survey to give you all the elements that you need before you start the detailed survey.
Cool. Thank you very much.
Thank you. Felicia, your hand is up. Please ask your question.
Thank you. I just want to ask, it's about this. You stated while you were presenting that different analytical methods could give different results about the same sample.
Yes.
So I'm quite intrigued about something like this, that what is giving rise to that? What is the cause, and how can one fix it? Does it mean there should be specific analytical results for different samples? Or because my own thoughts, I think you should be able to verify the result gotten from one analytical sample with another analytical sample for the same analytical method for the same sample, and it should be probably very close. So why the variance?
I mean, for example, I have shown the results with a cold MMI method. Okay.
Yeah. And the other.
You have seen that. So the concentrations there of lead were very, very low compared to the concentrations of hot aqua richer and compared to the total concentrations by XRF. Okay. So you have here essentially defining, first of all, 3 different backgrounds, 3 different thresholds, and 3 different anomaly levels, depending on which analytical method you are using. So it's very important. It's very important when you want to compare results, you must analyze the same grain size by the same analytical method. Okay, and if you are going to analyze samples from the same area, okay, and you are sort of to have done so a first phase of sampling, and you send the samples to the laboratory for analysis, and then you continue for a second season in the same area, and you send these samples to the laboratory for analysis, then you are in trouble. You may use the same analytical method, you may use the same laboratory, but you are not duplicating the same laboratory sort of conditions. The laboratory conditions between your first and second or third sort of batches are changing. Okay, so you have to introduce, for example, samples from your first phase, second phase, and into the third phase in order to see if there are any differences. Okay, because if there are differences, then you have problems. Because your results must be comparable.
Yeah.
So
Absolutely.
everything you have to do it with, with good planning and good thinking. Okay. This
Thanks,
is the unfortunate
Alecos.
thing that people do not realize these very subtle things.
Thank you. Monk, I may be mispronouncing your name. I apologize if I have it incorrectly there, but please go ahead with your question.
Hi, thank you. No, you pronounced it rightly. So, first of all, thank you for this nice event. And thank you, Dr. Alecos, for your...
Very nice seeing you.
Yes,
and I hope to
yes.
see you in Espoo.
Yes, yes, as well. Yes. So, just to quickly give my 2 cents on the last question is, you need to compare oranges to oranges for apples to apples, right? The different analytical methods. Yeah, I was just thinking of an analogy like that.
I did
Do
not
you agree?
understand your question.
So
I think it was an
that was just,
observation.
yeah, that was just my 2 cents based on your explanation.
Yeah, I think it was a very good observation, actually. I think it actually helps Felicia's question to a certain degree as well.
Okay.
Yeah. So, my question was, the rolling sampling method. I didn't quite get your explanation. I was thinking of our project and trying to formulate a question, an efficient question. But could you explain
this was
the
a
rolling
special
sampling again?
case. Be careful. This was a special case.
Yeah.
Okay, because the company wanted us to assess the contamination of each block.
Yeah.
Okay, so I had to relate the blocks. Okay, so the only way to relate the neighboring blocks, okay, is to, for example, the corner samples of the square to be subdivided, okay, in such a way so that each block has a certain portion of the neighboring block.
So, in essence, the one corner would be sampled like four times.
Well, at each point it was around each sampling point. Okay, the corner. I have taken 4 samples. Okay.
Yeah.
Four samples, but all these samples were placed in on the plastic bag. Okay. Then they were broken up and tried to homogenize them as good as possible in the field, and then separate them into quarters, or depending where the sample was, sometimes it was just halves and sometimes 1/3, okay, depending again on the surrounding blocks. And 1/4 was placed in one block, and the other quarter the other block, the other quarter another block. So there was a link between the blocks, okay? And the only difference for each block was the random site within each block. Okay, so within each block there was one sample, taken at random, which had nothing to do with the sample, the same sample taken in the next block, the neighboring block. Do you understand it?
More better picture. And
anyway,
so,
you'll have the presentation.
Yeah.
Okay.
Yeah.
I was about to suggest
and it's
exactly that. If you
explained.
go back and have a look, I think it'll
Yes,
probably get
and
you there.
if you do not understand it, send me an email and I will explain everything by email.
Yes. Okay. Thank you. Thank you.
Okay.
That's very kind.
Yes.
Thank you.
Or we can discuss it at ESPO as well.
Yes. Yes. Looking forward to it.
Yeah.
I
Okay.
don't see any further hands up. I'm very grateful to Alecos for having hung on for a bit of extra time. Is there anybody else who wants to ask a question? No. Okay, in that case, I just would like to say a huge thank you to you again for giving us an interesting talk. Personally, I found it fascinating, having been on that side of geology rather than some of the other work that you've done. Thank and a really interesting talk. Thank you. I think I possibly even know where you've been working, but it's probably worth mentioning at this particular point for the people who are very much academics that the work which you carried out there is typical of the work which is done on the back of pollution prevention control across the entirety of the EU for understanding what contamination might be on any industrial site. So it's work which is being carried out extensively, but the important point which you make is about the certainty of where you're sampling, why you're sampling, how you're sampling, when you're going to do it, what the background conditions are. All of those things are so important and really need to be brought into other people's work. So thank you for bringing that out in your talk today.
Thank you, Ilian. Nice to see you again.
And you too. Take care very much indeed. Thank you for attending, everybody.
Okay, bye-bye.
Bye.
Thank you, Alecos, sir.
Bye-bye.
It was nice seeing you.
Hello. How are you?
Hello, sir. All good, sir. How are you?
Fine,
It's a
thank